Good evening and welcome back to Bedtime Talks. Today, we're following 3 Atlas, a quiet traveler from another star, never meant to impress, never meant to change anything, just a cold relic drifting through our solar system along a calm, predictable arc of dust and pale light. But on October 29th, 2025, as it skimmed close to the sun, it gently broke the rules we use to understand comets. At first, the instruments showed nothing unusual at all, and then, in a single captured frame, everything shifted. A flare rose from the surface of 3 Atlas, sharp, clean, strangely geometric, and bright in a way that didn't feel accidental. Within minutes, 3 observatories across 2 continents reported the same burst, the same signature. What first? It looked like a calibration hiccup, became a confirmed event. What seemed like just a comet became a question that wouldn't settle. For about 20 minutes, 3 Atlas blazed beyond expectation, nearly 4 times brighter than the models. Allowed. Then, it dropped back into silence, its light curve flattening, abruptly, like a dial turned down, and its path shifted, just slightly, as if it had felt the sun's gravity, and answered back. In control rooms from Pasadena to Darmstadt, scientists held still over their consoles because the data looked clean and the geometry looked real. Inside that brief spike, there was something even stranger. Balance, where randomness should dominate, precision, where chaos should bloom. From that moment, 3 Atlas stopped feeling like a simple rock. It became an anomaly, a small message written in light from something that was never expected to speak at. You're listening to Bedtime Talks, calm stories, soft mysteries, told slowly, for late nights across the United States. If you're new here, you can subscribe and settle in with us. And if you'd like, tell me where you're listening from and what time it is for you right now. Now, let's return to the moment the sky changed its tone. At first, the safest answer was the simplest: a sensor glitch, a bright pixel, solar interference in the optics. But when 3 separate observatories confirmed the same spike, within minutes, disbelief turned into quiet focus. Something happened near the sun, something the predictive models for 3I Atlas didn't include and didn't know how to explain. This interstellar, the visitor should have brightened gradually as it rounded perihelion, then faded smoothly afterward. Instead, its luminosity jumped suddenly by a factor of 4. The spike lasted just under 20 minutes, then collapsed into a flat line, a riddle written in light. And to understand why that alarmed researchers, we need to remember what normal usually looks like. Normally, when a comet approaches the sun, heat wakes the ice near its surface. That ice turns into gas, and the gas drags dust outward into space. A glowing coma forms, the bright envelope around the nucleus, and sometimes a tail appears, streaming away from the sun. It's a dependable story. Closer means warmer, warmer means more activity. More activity means brighter. Then, after closest approach, sunlight weakens, and the comet begins to fade along a familiar curve. That's what every known comet tends to do. But 3 Atlas didn't follow that curve. At perihelion, around 0.17 astronomical units, the outgassing should have peaked gently. Instead, telescopes recorded an instantaneous jump in brightness, and the light didn't look like a growing haze, not soft, not diffuse, not cloud-like. It looked tight, sharp, concentrated. In scientific terms, it resembled an optical flare, a sudden outburst releasing more energy than simple solar heating should be able to produce. One team described it as non-thermal, meaning the output rose beyond what temperature alone could explain. At the same time, solar monitoring satellites detected a brief spike of ionized particles moving outward from roughly the same region of space. But there was a complication. From Earth's viewpoint, 3 Atlas was nearly behind the sun. Direct, visual confirmation was limited. SOHO's LASCO coronagraph frames caught only faint edges, like watching lightning through a thin curtain. In those few visible moments, the sequence looked eerie, a spherical expansion of gas, swelling outward, followed by a rapid collapse into a tighter, dimmer structure. The light curve flattened, and when the glare subsided, the object appeared dimmer than before. Astronomers began to test explanations. The most conservative idea was structural venting, a sudden rupture of pressure within the nucleus. If the interior held pockets of frozen carbon dioxide trapped beneath an insulating crust, perihelion heat could have triggered a sudden release, momentarily increasing brightness. That fit one key detail. This object appeared rich in carbon dioxide, far more than water ice. So the theory sounded reasonable for a moment, but even that struggled to explain the geometry, the mystery. After the outburst, the comet's trajectory shifted slightly. The eccentricity of its orbit decreased by a measurable fraction, as though momentum had been exchanged with something unseen. That shouldn't happen without an external push. Yet orbital solutions, confirmed independently by ESA and NASA teams, showed the change was real. Either the nucleus redistributed mass internally, or the outburst produced thrust strong enough to alter its motion. In either case, the flare wasn't only a visual surprise. It left fingerprints across multiple datasets, optical, infrared, and magnetic readings too. Energy released faster than theory predicted, shape where randomness should reign, and then silence, where lingering noise was expected. That night, one senior scientist reportedly murmured the same thought many felt. That shouldn't happen, and yet it did. Now, as 3 Atlas drifts away from the Sun, the question remains quietly unresolved. Was it a natural detonation of trapped volatiles, or the first sign that something inside this object behaves by rules I haven't written yet? Because almost everything in our solar system follows one invisible law. Gravity keeps things bound. Planets loop, comets return, asteroids repeat their paths, but 3 Atlas was never part of that pattern. From the moment it was discovered, its motion told a different story. Its orbit was hyperbolic, not elliptical, not even nearly closed. In mathematics, that means one thing: it's leaving, and it won't come back. When astronomers plotted its route in July 2025, the numbers were unambiguous. Its eccentricity, the measure of how open an orbit is, was greater than 1. Bound objects stay below 1. Above 1 means escape. 3 Atlas wasn't looping around the Sun, it was passing through. Like a stone skipping across dark water, it entered from deep interstellar space, curved under the Sun's pull, and will exit again, not returning, not in any human lifetime. That alone would have made it historic. Before Atlas, only 2 interstellar visitors were confirmed: Oumuamua in 2017 and 2I Borisov in 2019. But Atlas arrived with a twist. Its trajectory was almost aligned with the plane of the planets, just 5 degrees off the ecliptic. That angle is statistically rare. Most interstellar bodies arrive from steep, random tilts. Yet this one slipped in as if it knew the lanes. And there was another odd detail. It moved retrograde against the direction of the planets. While the solar system turns one way, Atlas traveled the opposite. That reversed motion complicates gravitational interactions and makes close passes less common. In other words, it didn't just look foreign, it moved foreign. Its inbound speed, roughly 42 kilometers per second, carried the fingerprint of another stellar nursery. And later, spectroscopy strengthened that impression. Carbon dioxide dominated its chemistry, far beyond what we see in typical catalogued comets. Its ingredients felt unfamiliar, and so did its behavior. Even far away, before sunlight should have awakened it, it was already active, venting gas, brightening early, ignoring the distance thresholds that keep ordinary comets dormant. It was awake too soon, like a lamp glowing long before evening. As it swung inward, astronomers expected a predictable rise, then a gradual fade. Instead, its light curve pulsed in uneven beats every few days, a rhythm that didn't neatly match rotation and didn't resemble typical outgassing cycles. It almost felt like breathing. Some researchers suggested internal layering, shells of volatile ices and tougher minerals, warming and venting in sequence. Others considered something stranger, resonance with solar magnetic fields, rare, uncertain, but not impossible in plasma-rich environments. During its approach, tracking networks watched it obsessively. At its closest, it passed within about 0.19 astronomical units of Mars, close enough for subtle gravitational nudges, far enough to rule out collision. Still, Its motion showed deviations, small, persistent, measurable, hard to explain, fully with jet thrust alone. Something about its mass, distribution resisted clean modeling. That's when a nickname began circulating in logs and internal memos. The hyperbolic stranger, not merely a comet, but a messenger from a region where chemistry and radiation shape matter differently. It carried the memory of another star, another epoch. By October 29th, at perihelion, its interstellar nature was no longer in doubt. The data suggested it was likely ejected from its home system millions of years ago, far beyond anything like our own Oort cloud. It crossed light years of darkness, collecting cosmic dust, radiation scars, and quiet secrets. Now, as it departs, fading toward the outer void, 3 Atlas becomes both visitor and teacher. Every photon it reflects carries chemistry from elsewhere, a place we may never reach. It reminds us the sun's gravity is powerful, but it's only one voice in a much larger choir, and every so often, one rare note drifts through, hyperbolic, brief, strange, and then disappears into the silence between stars. Comets are often called dirty snowballs, and usually that's true. Their cores are mostly water ice mixed with dust, rock, and organics. As they warm near the sun, that ice sublimates, turning from solid to gas, forming the coma, the glowing envelope. Water vapor is normally the dominant ingredient, always, until now. When James Webb turned toward 3 Atlas, scientists expected the familiar signature of water-driven activity, hydroxyl emission, hydrogen traces, ultraviolet fluorescence tied to H2O. Instead, they found something rare, a coma dominated by carbon dioxide. The CO2 to water ratio was roughly 8:1, meaning for every 1 water molecule, there were about 8 of CO2 in comet science. That's extreme. The kind of result that sends everyone back to the drawing board. Carbon dioxide becomes gas at much lower temperatures than water, so it can vent much farther from the sun, hundreds of millions of kilometers earlier than normal. That means 3 Atlas could begin releasing gas long before solar heat should have awakened typical ice. And the early observations suggested exactly that. Near 3 astronomical units, it was already venting heavily, awake far too soon. One theory suggests it formed in a colder region around its parent star, so cold that water stayed, buried deep inside, while carbon dioxide accumulated closer to the surface. If that's true, the object is almost an inverted comet, its chemistry flipped, inside out, its volatile layers arranged in a way solar system comets rarely develop naturally. And that quiet difference may be the reason this visitor keeps surprising us, even when it's trying to look calm. That carbon-heavy mix can explain why perihelion looked so wrong. When CO2 sublimates, it expands with more shove than water vapor, driving tight jets that can spin a nucleus or crack it open. But the usual aftermath never arrived. No wild, non-gravitational lurch, no obvious breakup, no drifting shards. Even with that fierce venting, 3 Atlas stayed strangely composed. Its track only nudged, slightly, measurably. That contradiction made astronomers uneasy. One calm possibility is strength, a denser, more cohesive body than expected, a CO2, rich crust, wrapped over something tougher beneath, rocky, or even metal-leaning, able to hold pressure without falling apart. If so, gas wouldn't burst from everywhere. It would slip through narrow seams, hairline cracks, hidden vents, a focused release, rather than a messy tantrum. That could also explain the near symmetry seen during the outburst, jets that looked balanced, almost coordinated. And another clue sits in what the spectra did not. The missing water lines suggest the surface never reached a state where water molecules could freely escape, even at perihelion. By the book, the sun should have awakened any exposed ice. So, if water stayed silent, 2 paths remain. Either the water is sealed deep down beneath an insulating shell, frosted, armored, and out of reach, or there simply isn't much water there at all. And if that second option is true, 3 Atlas becomes something we've barely ever had to. Imagine a comet with little to no accessible water, an object that doesn't run on the usual fuel. That would shake the labels, because traditional comet behavior is normally driven by water sublimation, Remove that engine, and the category starts to wobble, yet it behaves too actively, too responsive, to fit neatly into asteroid either, so astronomers are pushed into the grey space, revisiting the old taxonomy, comet, asteroid, interstellar visitor, and wondering if those boxes, more like a sealed container, a pressure vessel, carrying volatile gases from another stellar nursery, releasing them only when conditions turn extreme, and the missing water doesn't make it smaller in importance. It makes it disruptive, because comet science has long treated water as the baseline, the universal driver of motion, but 3I Atlas challenges that assumption, quietly, completely. CO2 without water shouldn't create a living comet, and yet it still glows, it still turns, it still surges near the sun, teaching us that unfamiliar chemistry can awaken when it meets our light, and when the outburst began, it didn't resemble a normal explosion. There was no crooked plume, no lopsided spray. Instead, through the harsh glare, telescopes caught something uncanny, a smooth swelling of brightness, expanding outward evenly, as if a clear sphere had inflated around the object. Astronomers gave it a simple name, the shell. It expanded, quickly, then seemed to pause, almost frozen, for several long minutes, before fading into the background. That defies the usual comet story. Most nuclei vent unevenly, sunlit patches, shadowed fractures, rotation making, everything irregular. Jets collide, dust scatters, the coma turns fuzzy and chaotic, but here, the expansion looked uniform, structured, almost calm. Solar orbiter measurements traced the shell's boundary to nearly 20,000 kilometers. Across, enormous, yet oddly sharp-edged, too, defined to be ordinary outgassing. And the light wasn't merely sunlight bouncing off dust. Spectral readings hinted at high-excitation carbon dioxide ions, CO2 mise lines, the kind that appear when molecules lose electrons under extreme ultraviolet conditions. In plain language, the gas didn't just evaporate, it ionized, becoming plasma, a thin, magnetized skin, pushing outward into the solar wind. Then came the detail that made people stare longer. The edge wasn't perfectly smooth. It carried 6 faint ridges, a whispered hexagon in the imagery. In plasma physics, 6-sided symmetry can emerge when electromagnetic forces settle into temporary balance. Cells like that can be recreated in labs, but around a comet, in open space, it's nearly unheard of. The timing, the symmetry, the geometry made random harder to defend. One grounded idea suggests multiple fissures vented together, nearly in phase. If pressure built broadly under the surface, the crust might split along stress lines, releasing gas in a synchronized expansion, less a chaotic blowout, more a coordinated release. In that picture, the hexagonal ridges could be boundary zones, places where opposing flows met and briefly stabilized. Another hypothesis looks outward instead of inward. Near perihelion, the sun's magnetic environment is a turbulent sea. When a dense pocket of plasma enters that sea, temporary boundaries can form, magnetized pauses, where forces balance for a moment, like a bubble holding shape. If Atlas released a large burst of ionized CO2, the solar wind could have sculpted it, compressed it, and briefly carved that 6-ridge pattern, a magnetic bubble, lasting only minutes, before dissolving into the solar current. Whatever the mechanism, the scale mattered, because the shell didn't only glow, it seemed to push back. Parker Solar Probe data hinted at a subtle downstream drop in proton density, as if the expanding envelope displaced part of the solar wind itself. That implies energy transfer larger than simple heat venting, not cosmic in size, but enormous for a small body only a few kilometers wide. The math points to a sudden release of power, small on a cosmic chart, but astonishing for a body only kilometers wide. And then, the aftertaste of it all. When the shell thinned and vanished, 3I Atlas didn't splinter the way many expected. It remained whole, yet dimmer, as if the event had stripped away a surface, layer, not crushed the heart of the nucleus. Some astronomers compared it to shedding, a quiet kind of molting, outer material loosening, and drifting off into space. That idea fits the light curve's story, a sharp rise, a brief steadiness, then a quick drop, as a bright, reflective coating dispersed and stopped helping the comet shine. And the shell may not have been only gas, because high-resolution photometry hinted at something mixed within it, tiny particles, dust grains at micron scale, glittering, briefly, some apparently coated with frozen CO2 crystals. Those crystals would vanish fast in solar heat, adding to the flash, while the dust lingered just long enough to scatter and fade, so the shell becomes a kind of bubble, CO2 vapor carrying a halo of microscopic mirrors, amplifying light for a moment, then slipping away. The whole episode lasted less than half an hour, but it bent our assumptions about comet structure. Before 3i Atlas, no interstellar visitor had shown this level of symmetry, or this calm under such brutal solar stress. Natural or not, the shell suggested something important. The surface isn't merely reactive, it's responsive, capable of uniform behavior when pushed to extremes. For a few minutes, near the Sun, 3i Atlas stopped acting like a messy comet and started acting like a system, a body releasing energy in patterned waves, as if the universe pressed a button we didn't know existed. Then the shell softened, the glow dimmed, and the traveler continued outward, quiet again, but no longer simple. Still, those minutes felt different, shimmering, structured, almost deliberate, and the timing pulled attention toward the Sun itself. On October 29th, 2025, the Sun launched a coronal mass ejection, a river of magnetized plasma thrown outward at immense speed. At first glance, nothing unusual. CMEs happen often, some gentle, some fierce, but what mattered wasn't the size, it was the aim. This CME rose from the Sun's southern hemisphere, along the same corridor 3i Atlas was traveling. As it reached perihelion, hours later, the comet erupted. 3 separate space observatories logged the sampling. Coincidence? And the question sharpened. In the dark, could the CME have triggered the outburst? And if it did, what does that say about comets and solar plasma? To hold the puzzle gently, we need to define the thing. A CME isn't just light, it's matter. Billions of tons of charged particles, laced with magnetic fields. When one sweeps past planets, it can compress atmospheres, warp magnetic lines, and sometimes disturb Earth's communications. When a CME passes a comet, it usually leaves a visible signature, a tail bending, hard, a coma flaring, sometimes even a tail being torn away. As happened in past events researchers still cite, but 3i Atlas didn't react like any familiar case. Solar wind monitors registered an impact, right as the brightness jumped, as though the strike and the flare arrived together. And yet, the CME itself wasn't extreme, a modest class by solar standards, too mild to directly explain the comet's enormous light output. So the CME may not have supplied the energy. It may have unlocked it, like a spark meeting a pressurized chamber. One model suggests the incoming plasma acted as a detonator. Picture the surface already stressed by sunlight, with pockets of CO2 ice under pressure just beneath the crust. As the CME's magnetic field swept across the nucleus, it could have induced electrical currents through any conductive regions. Even a tiny current density, spread across a whole surface, can create localized heating, fast sublimation, sudden rupture, and magnetic field oscillated at low frequencies. If the comet's interior held layered materials with different electrical conductivities, those oscillations might have coupled in a brief resonance, external field meeting, internal structure, building stress from within, until the surface failed, releasing energy without a direct impact in the usual sense. Solar physicists noted a historic detail. This may be the first measured encounter between a CME and an interstellar object. Previous comet interactions involved bodies born here, shaped by local chemistry, local dust, local magnetic habits. But 3i Atlas came from elsewhere, and its plasma behavior may not follow our usual expectations. A CO2 heavy envelope ionizes differently than a water-rich coma, potentially allowing charge to build instead of dispersing smoothly. In that case, a CME could cause more than pressure and heat. It could drive electrical breakdown, a kind of cosmic short circuit, and the timing kept leaning in that direction. LASCO C3 recorded the CME front, arriving near the comet around 1436 UTC. At roughly 1438 UTC, the light curve spiked by about 1450. Brightness steadied, then declined. No other solar environment event fits that sequence so neatly. It didn't feel random, it felt synchronized. Later, Parker Solar Probe data hinted at a ripple, a density disturbance near the same coordinates, consistent with plasma meeting plasma and resisting the flow. In other words, the comet pushed back. What makes this remarkable isn't just the idea, it's that instruments actually measured it, a moment of energy exchange between our sun and an interstellar traveler, not a collision of rocks, but a meeting of magnetic intentions. The CME arrived, the comet answered, and for 20 minutes, both systems seemed to sing the same note. Whether that was coincidence or perfect natural timing is still open. Some call it a normal resonance under stress. Others can't ignore how clean it looks, as if the comet was tuned to the sun's pulse. Either way, the CME connection turned a routine eruption into one of the strangest astronomical windows in comet recent memory. A quiet handshake, written in plasma, and then silence. And the story isn't only about what we saw, but what we didn't. For nearly 20 minutes during the closest pass, Soho's LASCO recorded nothing, a data gap beginning around 1437 UTC on October 29th, right when 3I Atlas brightened. When imaging resumed, the coma looked altered, and the surrounding plasma field seemed subtly rearranged. Those missing frames, now logged in the official archive, became a controversial silence. To an untrained ear, it sounds like a glitch, and maybe it was. Coronagraphs can enter protective modes when radiation overwhelms the sensor, pausing imaging to prevent damage. Engineers say it's routine, not drama, not secrecy. Mission scientists have explained it plainly. If brightness saturates the field, the camera safes itself, not a cover-up, just survival. But the problem isn't the mechanism, it's the timing. These safing events align with major flares or particle storms, yet that day, no X-class flare, no large radiation spike, no blackout, solar flux indices stayed relatively stable, no broad disturbance, no obvious reason for a long shutdown, and the only standout event near that window was the comet's outburst itself. ESA analysts reviewed telemetry logs and saw something telling. LASCO exposure settings saturated, exceeding thresholds by roughly 7 times, and the automatic safing sequence froze imaging. When the system returned about 20 minutes later, the brightness had already calmed. This is exactly what you'd expect if something extremely bright in a small, localized region briefly entered the frame, brighter than the surrounding corona in key pixels. But what could shine like that without tripping other nearby sensors the same way? The honest answer is still uncertainty. And uncertainty feeds stories. Within hours, social media filled the gap with certainty. Claims of deletion, censorship, hidden footage, screenshots of missing timestamps, red circles on static frames, insisting a geometric object appeared before the blackout. None of it verified, but the pattern is familiar. The less data we have, the louder the theories become. For astronomers, the missing frames debate highlights something deeper: our dependence on continuity. SOHO was built for precision, not narrative. When data vanishes, it's usually mechanical: radiation, hits, buffer overloads, telemetry faults, common risks close to the sun. Still, the overlap here is uncanny enough to create the illusion of a story written on purpose. Independent teams tried to reconstruct the timeline using other spacecraft: Stereo A, Solar Orbiter, Parker Solar Probe. Parker confirmed a density wave consistent with an energy release, but none of the other cameras had a clear line of sight. So one of the decade's most important moments remains visually undocumented. A small, Max Planck group attempted a reconstruction using solar wind density patterns before and after the blackout. They inferred a temporary expansion of the comet's plasma envelope, suggesting the brightness surge could have saturated LASCO's CCD, blinding the instrument. In that reading, it wasn't censorship, it was physics. The comet overwhelmed the camera with light. Still, questions linger softly at the edges. Why did safing last around 20 minutes, not the typical shorter pause? Why did internal temperature readings rise? Only modestly, not enough to justify a full halt on their own. And why do a few late-gap frames show compression artifacts, horizontal banding, that some associate with constrained telemetry? Conspiracies love a gap, but even skeptics admit the timing feels improbable. One engineer's remark captured the mood. You could image the sun for decades and rarely lose a 20-minute window that perfectly overlaps a once-in-a-lifetime interstellar event. It reminds us the frontier is fragile. Sometimes mysteries aren't hidden, they're lost in the blink of a sensor. Maybe we didn't lose the data at all. Maybe we reached the ceiling of what our machines can tolerate. Whatever happened inside those missing. Instrument overload, perfect coincidence, or something unnamed. The silence stays louder than the images. The universe flickered, our cameras looked away, and when they opened again, 3I. Atlas was not quite the same. In the hours after, as teams sifted spectra and particle counts, one detail kept returning. A strange feature in magnetic readings near the sun. Instruments aboard SDO and Parker detected a faint but measurable oscillation in the heliospheric magnetic field. It wasn't messy. It pulsed, about every 9 seconds, persisting for nearly 12 minutes, then disappearing, and the timing aligned almost exactly with the comet's burst window. Most would label bit background turbulence, but a few saw something else, a resonance. The sun's magnetic field is a restless ocean, loops and currents twisting through the corona, storms flinging energy across vast distances. A comet in that environment is usually passive, shaped by the field, carved by the wind. But on rare occasions, the interaction becomes two-way. The comet's own plasma can couple with the solar field, creating feedback waves, ripples meeting ripples, amplifying when frequencies align. That's magnetic resonance. 2. Oscillating systems briefly vibrating as one. And with 3I Atlas, the alignment seemed uncomfortably close. Those 9-second pulses match a predicted nucleus spin period within a few percent, meaning rotation and solar magnetics may have synchronized in frequency for a short time. If so, energy could transfer efficiently, not as a blunt impact, but as induced excitation, like one tuning fork waking another at the same pitch. The sun provides the tone. The comet answers back. For a few minutes, Atlas may have absorbed more energy than its surface could safely hold, and when the coupling broke, the stored stress could have released as gas, light, and structured plasma. The outburst we witnessed, resonance effects, aren't fantasy. Voyager and Juno have recorded similar principles near planetary magnetospheres, standing waves, current sheets, temporary magnetic mirrors, structures that trap particles when conditions align. Parker's data hinted at mirror-like behavior near the comet's estimated position, a compression, then relaxation, as if the sun's magnetic heartbeat briefly stumbled. This idea also fits the shell's shape, a magnetized bubble formed by resonance pressure, plasma trapped inside, glowing as it cooled, with hexagonal hints where currents folded and balanced. Lab simulations under alternating magnetic fields can produce comparable cell-like geometries, but then the mystery deepens. Large-scale resonance needs conductivity, and plenty of it. Typical comet material, rock and ice, is a poor conductor, yet the coupling implied here suggests regions of unusually conductive material inside 3I Atlas, metal-rich veins, carbon-rich, crystalline structures, something that can carry current like a supercooled circuit, less snowball, more battery. When scientists mapped the oscillation phase, another curiosity appeared, a quarter-cycle lag, a signature often linked to inductive coupling, where a secondary system doesn't only absorb energy, it briefly stores it and then re-emits it. In simpler terms, Atlas may not have only received the sun's pulse, it may have returned one. That could also explain the faint, shock-like wave Parker detected. Afterward, when resonance slipped out of phase, stored energy would dissipate quickly, sending a pulse into the surrounding solar wind, measured as a localized density increase, traveling outward from near the comet's coordinates. Skeptics are right to caution. Correlation isn't causation. Solar plasma is noisy. Fluctuations happen constantly. But even cautious researchers admit this alignment is the kind that keeps people awake. A harmonic signal, matching the comet's spin, present during the burst, gone afterward, too neat to ignore completely. Whatever the true explanation, one fact remains. For a short window, the sun and an interstellar visitor shared a frequency, fields, intertwining, energy passing between them, then silence. Again, leaving only the echo of a pattern too precise to dismiss easily. After the light faded and the comet moved outward, many assumed it had fractured. That would have been the sensible ending. Comets, under that kind of stress, often shed fragments, little pieces trailing behind like embers. Early infrared views from solar orbiter even seemed to support it. Multiple reflective points near the path. Headlines rushed in. Breakup near the path. Sun. But within 48 hours, the story started to unravel. Those points didn't behave like debris. True fragments drift apart, small pieces separating faster, spacing, widening in a predictable spread, a faint trail forming over time. Here, the points held their spacing, staying arranged relative to the primary nucleus, in a tidy geometric formation, stable for more than 20 hours. That's not how rubble moves. That's closer to how bound companions move. Scientists at ESA modeled the positions, the solutions suggested. The secondary points were gravitationally tied to the main body, not freely dispersing, which is strange. A nucleus under 2 kilometers across shouldn't have enough gravity to hold even tiny fragments against solar radiation pressure, so something else might have been maintaining the formation. One proposal was magnetic cohesion. If the outburst created a sheath of ionized dust grains, charged particles can clump into filaments and sheets, structures that mimic solidity and can rotate in step with a central source. That could explain why the points appeared to move together, as if connected by invisible threads. Another, more daring idea arrived from radio monitoring. The Allen telescope array reported faint intermittent bursts around 2.8 to 3.1 gigahertz, a band often associated with radar-style backscatter studies. The signal wasn't clearly coded, not neatly structured, but it pulsed on intervals that matched the nucleus's estimated spin, period. And in the soft quiet, after all that data, the same question returned, not loud, just persistent. What exactly is traveling with 3i Atlas as it slips back toward the dark? At first, the team waved it off as interference, a familiar kind of background noise. But later, 20, a brightness more like metallic meteorites than dusty ice and grit, yet the spectra didn't shout iron or nickel or silicates, no sharp fingerprints of familiar metals. Instead, the curve was flat, quiet, consistent with heavily carbonized surfaces or amorphous composite material, maybe even glassy in texture. Some wondered if CO2 frost crystals briefly coated the pieces, turning them mirror-like until sublimation erased the shine. Others offered a different possibility, that they weren't pieces at all, but coherent clumps of plasma, magnetic knots left behind after the outburst. Plasma instabilities, like Birkeland currents, can form bright regions that look solid, while being entirely electromagnetic, lasting hours, sometimes days, before thinning into nothing. Still, a smaller group entertained something more exotic. If the geometry held steady, and the reflectivity repeated with near mathematical regularity, that persistence could hint at structure, objects with integrity, rather than loose debris. No dataset confirms that, not yet, but the symmetry stayed uncomfortably precise. 3 points, forming a near-perfect triangle, rotating with the nucleus at an almost constant angular rate. Nature can create order, but it rarely holds it for so long. By mid-November, the formation softened, the reflections dimmed one by one, until only the primary nucleus remained. Whether they sublimated, dispersed, or simply lost the right alignment, no one could say with confidence. The last high-resolution VLT image showed a faint haze instead, a thin cloud of microparticles trailing gently behind the main body. In official bulletins, the language stayed neutral, transient, reflective substructures, careful words, meant to describe without implying. But inside research circles, it picked up another name, the formation event, not because the comet broke apart, but because it seemed to form something, briefly, precisely, and then dissolve back into the dark. If those lights were true fragments, they bent the rules of motion we expect, and if they weren't fragments, then they belonged to something stranger, the leftover shape of a process we don't yet understand. For weeks after the outburst, scientists wrestled with a simple question: how dense is 3 Atlas? It should have been straightforward: brightness, volume, outgassing rate, and how the object responds to solar radiation, pressure. Yet the numbers refused to agree. It behaved both heavier and lighter than it should. heavy enough to resist being pushed, yet porous enough to glow with activity, as if it carried two physical personalities at once. Traditional comet models, to assume densities around 0.3 to 0.6 grams per cubic centimeter, lighter than water, airy like packed snow, fragile bodies that vent gas and drift slightly off course. But 3 Atlas wouldn't follow that script. Despite releasing immense CO2 and dust, its trajectory barely budged. Outgassing calculations said, if it were as light as a typical comet, the jets should have nudged it measurably. Instead, it held its line, suggesting a higher mass, perhaps several times higher. Some estimates pushed its bulk density above 3 grams per cubic centimeter, denser than solid rock, closer to a metallic asteroid than a classic comet. But that creates a contradiction. If it were truly that dense, surface gravity and tensile, strength should have resisted violent venting, and yet the jet still escaped, freely, repeatedly. So which is it? Lightweight and volatile, or heavy and stubborn? Astronomers turned to indirect clues, coma brightness, mass loss rates, and the far, strange absence of measurable acceleration. 2 opposing answers emerged. Either the nucleus was extraordinarily massive, or the thrust from escaping gas somehow cancelled itself. Both feel unlikely, and yet one must be closer to the truth. Then a radical idea arrived from plasma physicists. If the jets vented symmetrically, in opposing directions, their forces could balance, leaving almost no net push. But that would require near-perfect vent symmetry, a natural improbability, unless the internal structure enforces it. Some suggested a core divided into lobes, or chambers, releasing gas in matched pulses, each vent offsetting another, a balanced engine, without intention, yet strangely effective. Another theory, more controversial, argued the nucleus, might not be uniform at all, instead dense inclusions embedded in a porous matrix, metal-rich pockets, anchored inside a CO2-heavy shell. That would explain inertia and still allow responsive outgassing. Warmth would awaken the porous zones first. Gas would slip out through weaker seams, while denser pockets acted like anchors, holding momentum steady. This could also connect to the rotational slowing recorded after the outburst, mass shifting inside, absorbing angular momentum, like a gyroscope under stress. Polarimetric studies added another hint. Most comets show predictable polarization curves, but 3 Atlas didn't behave consistently. It reflected light as though dust grains carried a thin, metallic film, bright at low angles, darker at high, a signature sometimes seen in conductive or coated particles. That signature could arise from interior material rich in carbon, nickel traces, or conductive alloys, materials capable of interacting with magnetic fields. If confirmed, 3 Atlas becomes neither comet nor asteroid, but a hybrid, a composite body from a system where metals and volatiles form together. Such environments are considered rare, even across the galaxy. Young, metal-rich stars, with cold, carbon-dense disks. In that sense, 3 Atlas would be a fossil, carrying the architecture of another sun, a relic shaped by a history unlike ours. And still, the paradox remained. When trajectory analysts recalculated mass from the minimal non-gravitational acceleration, they arrived at densities too high to support sublimation at all. By logic, it should be inert, and yet it breathes, rotates, flares, and glows. Some researchers began to treat the flight density paradox as a signal that models are missing something. Perhaps density alone doesn't govern motion inside a charged environment near the sun. Electromagnetic coupling can mimic added mass, letting an object resist acceleration without being physically heavy. In other words, it could look massive because it's magnetically tied to the surrounding field, a plasma interaction pretending to be stone. Whatever the mechanism, 3 Atlas stands out as the first known object to, about 32 seconds, rising abruptly, holding, then dissolving into background hiss. The timing matched the expanding plasma shell seen in optical data almost perfectly, and researchers realized this wasn't ordinary interference. They were hearing what looked like a plasma echo. A plasma echo is rare, almost shy in nature. It happens when disturbed charged particles reorganize, storing electromagnetic energy briefly, like tension held in an invisible spring, and then, after a delay, releasing it as a faint secondary wave, the plasma equivalent of a room ringing after a bell has stopped. The first reports came from Owens Valley in California, tracking solar background noise, when the instruments picked up an unusual harmonic sequence. Peaks, spaced evenly, as though the plasma itself were oscillating like a plucked string. Minutes later, confirmations arrived from Chile, South Africa, Japan. All saw the same basic pattern, with intensity differences based on viewing angle to the sun. When combined, triangulation pointed to one origin, the coordinates of 3 Atlas. Right as it re-emerged from behind the sun, the spectral fingerprint didn't match ordinary solar causes. Solar flares tend to be chaotic, noisy, irregular. This signal, though brief, was clean, repeating, and it faded with a mathematical decay curve consistent with damped plasma oscillations. It suggested something around the comet, absorbed energy from the CME, held it, then let it go, as an electromagnetic pulse. Physicists leaned in. If the coma, rich in CO2 ions, acted like a resonant cavity, it might have trapped charged particles briefly when the field relaxed. Electrons could have oscillated collectively, producing the observed echo. In laboratory plasma chambers, similar effects appear when dense ion clouds meet oscillating magnetic fields, an emission that carries the memory of the initial disturbance, but the detection range created a problem. For stations across half the Earth to catch it, plasma density had to be higher than expected, implying the coma was thicker, more conductive than a typical cometary gas cloud. Some proposed a temporary, magnetized envelope, strong enough to store and release energy like a capacitor. The waveform added another layer, 3 distinct peaks, evenly spaced, a triple pulse echo. In physics, that pattern often hints at geometry, energy rebounding between layered regions, as if the coma had stratified into shells, humming once, twice, 3 times, then fading. No one could recall another interstellar visitor doing anything like this. Even 2I Borisov, unusually active, never produced a detectable radio echo. So 3 Atlas became a new category, post-event plasma resonance, a behavior class all its own. A team at MIT's Haystack Observatory processed the spectrum into audible sound, and what emerged was, quietly, haunting, a deep rising tone, followed by 3 quick descending pulses, like a sonar ping traveling through dark water. For outreach, they called it the voice of Atlas, and while poetic, it wasn't entirely wrong. The echo was literally electromagnetic, an after-sound of energy exchange between the Toipola, sun and a visitor, evidence that Atlas wasn't only reacting chemically, but responding electrically to solar plasma. The signal ended as abruptly as it began, folding back into the ordinary radio whisper of the solar wind, but it left a fingerprint behind. 3 harmonic peaks in a perfect ratio, filed into archives around the world, an echo of a moment when 2 systems briefly spoke the same language. It began like a footnote, buried in magnetometer data from NASA's Messenger archive and ESA's Bepicolombo logs. On the day Atlas burst, Mercury's magnetic field recorded a faint transient, just over 90 seconds, barely above the noise, until timestamps were synchronized. Then the implications surfaced. Almost absurd. Mercury, nearly 58 million kilometers away, had flinched. Its weak field is extremely sensitive to solar changes, sitting in harsh electromagnetic weather, a magnetosphere that shifts like a heartbeat. CMEs usually leave clear signatures, but this one looked different, not like a typical flare impact, more like a brief shadow in the field, a downward dip, then rebound, as though something dense in plasma had brushed the lines aside. Scientists call these magnetospheric depressions, often caused by sudden plasma density increases that compress magnetic lines inward. Yet no ordinary solar wind shock was recorded then. Speed steady, density unremarkable, and the only density notable event close to that window was Atlas itself, erupting minutes earlier. The connection seemed impossible at first. The separation was vast, the comet nowhere near Mercury's orbit, but modeling the CME's propagation suggested secondary field effects could stretch toward Mercury, carrying remnants of the comet interaction, a ripple transmitted through solar plasma. In essence, When the CME struck the comet, a localized distortion formed and the disturbance traveled outward. Mercury happened to sit near the same field corridor, receiving a delayed echo, similar to how Earth sometimes records secondary ripples during intense storms, though never before linked to a single transient interstellar body. The arrival time, about 90 seconds after, the burst fit modeled magnetic wave speeds in that region, near 500 kilometers per second, and then another trace appeared. Bepi Colombo's ultraviolet spectrometer captured a brief darkening in scattered solar light. For 3 consecutive frames, just over a minute, a narrow linear drop across Mercury's dayside limb. Not an eclipse, not a simple glitch. It moved too quickly, then vanished too cleanly, almost like a shadow sweeping across the planet. Mercury has no thick atmosphere to catch a shadow like that, so the leading idea turned electromagnetic. When dense plasma crosses magnetic fields, it can refract radio and ultraviolet waves, creating localized absorption zones, a shadow not of light, but of resonance. In that sense, Mercury briefly wore an imprint, a distortion carried through the sun's lower corona, and the comet's outburst became not a local flare, but a system-wide tremor. For planetary scientists, the implications are quietly thrilling. Small, transient events may reverberate across orbits, space thunder after space lightning. The shadow on Mercury could be our first measurable sign of energy transfer between interstellar matter and solar plasma on a planetary scale. When presented at the European Planetary Science Congress, reactions split. Some called it coincidence, a background fluctuation dressed up by timing. Others argued probability was extremely low, less than 1 in 10,000, and they gave it a poetic name, the magnetic handshake. In the end, nothing visible remains. No residue, no mark, no crater, only a blip in magnetic memory, a whisper in ultraviolet, and timestamps that align too neatly to ignore. For 90 seconds, on October 29th, a planet closest to the Sun may have felt the breath of an interstellar traveler without ever seeing it. When 3 Atlas emerged from solar conjunction, many expected fireworks, a bright, ragged tail, the showy aftermath of surviving perihelion. Most comets that endure close passage shine intensely afterward, residual heat driving more venting. But when cameras returned on October 30th, they found something closer to absence. The object was there, faintly, yet muted, stripped, quiet. The traveler that had briefly outshone predictions now glowed like a distant ember. This became known as the optical silence. In astronomy, silence rarely means nothing. It means whatever is happening outside our easy view. The dimming wasn't slow. Within hours, its visual magnitude dropped by nearly half, implying either catastrophic breakup or sudden stabilization. Yet neither fit. Light curves stayed steady. No obvious tumbling, no frantic shape change, and radar pings confirmed a solid nucleus. It hadn't vanished. It had simply gone dark to the eye. That contradicted typical post-perihelion behavior. After a burst, residual heat usually drives secondary venting, dust lifts, reflectivity rises, comas grow, but Atlas produced a thin, uniform, strangely static dust trail, like an old contrail fading in still air. The simplest idea was exhaustion, that it spent its volatiles in the outburst and cooled into inertness, but spectra disagreed. Infrared instruments still detected faint CO2 emission. Activity continued, just without dust. And dust is what makes comets visible. Gas alone can be nearly transparent in optical light. So, Atlas became an active body that spoke, mostly in infrared and radio, a comet we could measure, but barely see. Some called it self-shadowing, suggesting the outburst left behind a fused carbon layer, a thin, glassy crust, formed as CO2. Ice flashed off and residue recondensed as dark carbon. Film, black, non-reflective, absorbing sunlight instead of scattering it. Lab work on CO2, rich residues, supports the possibility, under intense heat, carbon-rich dust can fuse into amorphous films with very low albedo, others pointed. Again to electromagnetics. If the surface accumulated charge during resonance with the sun, it might have rearranged dust into a cohesive layer, Electrostatic sorting can smooth and seal surfaces, changing reflectivity, without stopping sublimation beneath. In that picture, Atlas wasn't dead. It was cocooned, a blackened shell trapping volatiles within. Optical silence. Then isn't absence. It's transition, a body sliding into a new equilibrium, radiating more of its energy in longer wavelengths, invisible to eyes, visible to instruments. And in fact, infrared follow-up suggested it still glowed there. The psychological effect was real. For weeks it had been spectacle, then quiet. No bright tail, no color, only dim persistence. It felt almost poetic, an alien traveler refusing to perform for our vision, reminding us that visibility isn't the same as presence. Some compared it to plasma discharge behavior, where glowing gas transitions abruptly into a non-luminous state when balance is restored. If the burst was partly electrical, then fading could mark the system stabilizing. The shell neutralized, the current settled. By November 2nd, brightness stabilized near magnitude 13, too dim for most amateur scopes. Yet infrared detections continued, suggesting the engine still ran quietly. For scientists, this was the shift. Atlas stopped being a show and became a deeper mystery, optical. Silence wasn't an ending. It was a threshold where light, matter, and magnetism blurred together beyond easy sight. One day it spoke in flares and geometry. The next, it whispered only in heat. And somewhere beyond the sun's glare, it kept moving, intact. When it finally returned, clearly from conjunction, ground observatories noticed something subtle and strange. Its brightness profile didn't only dim, it changed character. Photometric analysis suggested its albedo increased, even as overall luminosity decreased, reflecting light more efficiently, but from a smaller, altered surface. They called it the reflectivity shift. A body growing dimmer, yet becoming more reflective, sounds contradictory, unless geometry, composition, or texture changed dramatically. And that is exactly what many now suspect occurred during perihelion. The burst may have stripped away dark carbon-rich coatings, exposing fresher subsurface ice or crystalline minerals beneath. A cleaner surface, smoother, more uniform, would scatter sunlight differently, brighter per unit area, even if less area was actively producing dust. Comets are often among the darkest things we know, their surfaces baked by radiation, coated in tar-like organics, tholins that absorb visible light, making the nucleus almost black. If those layers were suddenly removed, the underlying material would reflect far more effectively. Spectroscopy and polarization offered support. VLT instruments detected a polarization change after the burst, before perihelion, negative polarization typical of dark, porous terrain. Afterward, a reversal, often seen when light scatters from smoother, more crystalline surfaces, a hint of unweathered material newly revealed. The mechanism is still debated. Some argue solar heat did the stripping, others say pressure and mechanical blow-off did it faster. If the second is true, Atlas behaved like an ablating spacecraft, shedding an outer coat under stress, briefly, revealing a surface untouched since it left its home system. Another layer arrived in color. Pre-burst, a greenish tint typical of carbon-based emissions. Post-burst, the balance shifted toward neutral white, the green dulling, not disappearing. While reflectivity strengthened in near-infrared, consistent with silicate minerals, or icy grains dusted with thin frost, some suggested gas recondensed as frost on shadowed regions of the nucleus, temporarily boosting reflectivity. Others proposed electrostatic charging realigned dust on microscopic scales, a natural polishing in vacuum. But one of the most intriguing clues came from phase curves. Brightness now varied more sharply with solar angle, a trait linked to specular reflection. Light bouncing in preferred directions, rather than scattering softly. In simple terms, it began to reflect a little like metal, not like loose dust. No comet has shown optical coherence quite like that. Either the burst created smooth, glass-like ice layers, or it uncovered reflective strata, long buried beneath dark insulation. The shift changed the comet's apparent texture too. Before perihelion, the coma looked grainy, diffuse, dust-filled. Afterward, the coma thinned, and the nucleus edges appeared sharper, in high-resolution imagery, suggesting dust production dropped while surface brightness per area rose. The comet was no longer wrapped in haze. It looked bare, cleaner, more defined. Some physicists went further still, wondering if part of the reflectivity could be an electromagnetic effect for plasma and charged dust forming transient plasma mirrors that bend or enhance light briefly. If a residual field lingered from resonance with the sun, some of what we see might be refraction through charged gas, a kind of optical sleight of hand. But regardless of mechanism, the transformation seems real. The object that entered perihelion was dark, organic, turbulent. The one that emerged looked calmer, brighter in texture, and newly revealed. Astronomers compared it to a gemstone after cutting, outer soot removed, inner structure exposed. For a traveler, millions of years in flight, that kind of sudden resurfacing feels quietly poetic, a cloak shed in a single flare of light. Three-Eye Atlas may have crossed the galaxy, wrapped in the residue of its birth, only to lose that skin here, near our sun. What we see now may not be what it was, but what it truly is, a mirror of sunlight, and of the clarity that sometimes follows a storm. And then, as Solar Orbiter delivered its newest images, analysts noticed something else, something subtle, buried inside the data, small, but impossible to ignore, because even in the quiet, Atlas keeps leaving signatures, soft marks, in light and in the spaces between. And then, hidden inside the newest frames, a shape emerged that didn't look like ordinary dust at all. A plume, spiraling outward for thousands of kilometers, not a messy tail, not a scattered fan, but a structured ribbon, calm, coherent, rhythmic. It curled, like slow smoke, in a place with no air, a precise helix, turning, as if the comet's own rotation was drawing it into space. Later, researchers gave it a name, a spiral jet, a rotating filament of gas and plasma, pulsing in step with the nucleus itself. At first, it was barely there, only visible after careful enhancement. But, once the glare was peeled away, the geometry became undeniable, a corkscrew unfurling, with the same pitch angle, frame after frame after frame. That regularity matters, because random venting doesn't keep rhythm like that. Most comets cough, unevenly, impulsively, creating turbulence, not order. This looked almost engineered by physics, quiet, consistent, deliberate. The timing told an even stranger story. Each full rotation of the nucleus seemed to lay down one full turn of the spiral, as if the source point on the surface never wandered. A single stable vent, or narrow fissure, locked to one spot, rotating like a lighthouse. But the scale was breathtaking. A tiny opening, feeding a vast, continuous structure. Normally, outflows spread and dissolve, yet this one persisted, as though an unseen hand was guiding its shape. Plasma physicists leaned toward a magnetic explanation. If the escaping gas was ionized, then it wouldn't simply drift. It could follow field lines, as conductive. CO2, rich material, met the solar wind. An induced magnetic field could form around the comet. Rotation, ionization, magnetic tension, all braided together, and a corkscrew configuration becomes natural, not common, but possible, under just the right conditions. To test it, teams ran magnetohydrodynamic simulations, and the results were uncomfortably close. A rotating body, even with a weak magnetic moment, can generate a spiral jet when first outgassing rate and solar wind flow align. Precisely. The model predicted something else, too. Charge layering, positive ions toward the outer edge, electrons nearer the core, and that separation should create uneven glow, a soft pulse that comes and goes, and then, the observations answered. Back, stereo, time-lapse sequences showed flickering, steady, rhythmic, every 6 seconds, the same as the nucleus's measured rotation period. Not random shimmer, but a repeating beat, like a quiet metronome inside the plasma. Even more subtle, inside the coils, were thin, microfilaments of dust, threading along the plasma paths. Appearing as delicate luminous strands in polarized light, they wavered slightly, as if vibrating under tension. A few researchers suggested alpha waves and magnetic ripples traveling along the structure. Those are usually associated with the sun's corona or with planetary magnetospheres, not with comets. If that interpretation is right, then 3 Atlas wasn't behaving like a small icy body at all. It was behaving like an electromagnetic participant. Spectral analysis sharpened the picture. The spiral carried enhanced carbon and oxygen ion bands, not water, not hydroxyl, evidence of carbon dioxide plasma dominating the flow, and the lack of neutral molecules implies electrons were stripped almost immediately. Meaning, the jet wasn't merely gas, it was electrically alive. Over days, the spiral stretched farther, tens of thousands of kilometers into the solar wind, and slowly thinned, and finally faded. But it left a legacy in the data, proof that Atlas could channel energy not as chaotic splatter, but as rhythm, as structure, as repeating form, like a pattern the environment could read. And that raises quieter questions that don't settle easily. What kind of interior allows such behavior? Is there a conductive core, a lattice of material beneath the crust, a hidden scaffolding for magnetism? Or was this order simply resonance, rotation aligned with the sun's electromagnetic flow, a moment when timing and plasma fell into the same groove? In one final report, a researcher described the jet as a thread stitched through sunlight, and that phrase spread quickly because it captured what people felt, wonder, mixed with unease. If natural processes can do this, then interstellar comets may carry behaviors we've simply never seen in local bodies. And if it wasn't entirely natural, if the symmetry was too steady, too clean, then the comet becomes something else in our minds, not just a visitor, but a demonstration, a cosmic mechanism showing that geometry can survive inside chaos. For now, all we truly have is the record, a rotating nucleus, a pulsing jet, a spiral written into plasma, drifting into darkness. It's hard not to feel the suggestion that Atlas was spinning, not only through space, but in time with something larger, invisible, ancient, immense, a silent dance between fields, choreographed by the universe itself. 2 days after perihelion, Parker Solar Probe sent back its next packet of readings, and analysts noticed a new anomaly, a sudden spike in plasma density, a compression of magnetic field lines, followed by a brief, symmetrical dip, less than 40 seconds. Total, the waveform looked familiar, but the sun was quiet, no flare-driven shock, no obvious eruption, and the direction pointed away from the comet's position, as if 3 Atlas had launched a pulse of its own. Shock waves in space aren't sound, they're pressure and magnetism. Traveling through plasma, a sharp front where charged particles compress and heat, moving faster than the local alpha speed. They're usually born from huge events, solar eruptions, planetary bow shocks, supernova debris. A comet should to be too small, too fragile to make one, and yet the numbers wouldn't move. At 1446 UTC, moments after the outburst, Parker's magnetometer recorded an 18% jump in magnetic field strength and a 5-fold rise in proton density, a textbook signature of a passing shock front. The timing matched the window recorded by SOHO, and the direction vector traced back to 3 Atlas's coordinates. A pulse propagated outward near 600 kilometers per second. That isn't a casual fluctuation. It's a defined event. It's the kind of signature we associate with an explosion, and that leads to an impossible-sounding question. How does a kilometer-scale comet create a shock wave without tearing itself apart? The leading explanation returns to plasma interaction. When the CME slammed into Atlas, it could have ionized huge amounts of CO2 around the nucleus, turning the coma into a temporary magnetized cloud. That cloud, expanding rapidly into the solar wind, would create a discontinuity, a boundary where density, temperature, and magnetic pressure shift abruptly. And boundaries like that can become self-propagating, a magnetic shock. To picture it gently, imagine a pebble dropped into a still pond. Only the pond is plasma, invisible, flowing, and the pebble is electromagnetic coupling. For a brief moment, the comet's ionized envelope and the sun's field may have behaved like one coupled system, energy exchanged, tension stored. and then released into the heliosphere as a traveling front, carrying information about the impact. There is a distant precedent. In 2007, when a CME struck Comet Encke, a disconnection event was observed. Its plasma tail torn away, kinked, swept, downstream. But Atlas was different. No obvious tail disconnection. Instead, a symmetrical compression wave expanded like a bubble, detected by Parker, and also hinted at by solar orbiter instruments trailing, millions of kilometers away. 2. Spacecraft, 2 vantage points, 1 shared pulse. And it didn't end there. Locally, the solar wind slowed by nearly 5% for several minutes, as if dragged, then rebounded, accelerating again, with faint oscillations afterward, echoes that persisted for hours. 4. Heliophysicists. It was a rare natural experiment, an interstellar object behaving like a miniature magnetized engine, yet the energy budget still refuses to feel comfortable. Based on Parker's readings, the shock carried about 10 to the power of 15 joules, small by cosmic standards, but enormous for a comet this to size. Some researchers suspect resonance amplification, CME field, and induced field aligning briefly, magnifying the interaction, and when the alignment snapped, stored magnetic tension discharged in an instant. What's haunting is the comet's calm afterward. When visual data resumed, 3 Atlas appeared intact, still rotating, coma reshaped, but nucleus whole. It absorbed a storm, released a wave, and survived. If the pressure was mechanical, fracturing would be expected. But if it was magnetic, the stress could pass through space around it without breaking the body, like a vibration through a field. For days, a faint ripple continued outward, a subtle density trace in the solar wind. By the time it approached Mars's orbit, it dissolved into background noise. But in the archives, its fingerprint remains, a symmetrical pulse, born from a traveler that shouldn't have been able to make one. For the scientists watching, it felt less like a curiosity and more like a quiet warning. Interstellar bodies may not be passive stones when they enter a star's active plasma environment. Under precise conditions, they might interact energetically, even violently, shaping the space around them for a moment. Atlas's shockwave becomes a statement, an echo of the sun, answered by something foreign, and still, the comet seemed unscarred, as though the event happened in fields, not in fractures. A wave born, not from shattering rock, but from magnetism, tightening and releasing. A pressure that shakes plasma, while leaving matter strangely untouched. And that resilience is what keeps the story awake in the mind, because it suggests a visitor that can endure conditions our models don't expect it to endure. When astronomers traced the dust trail after perihelion, they expected a familiar picture, a diffuse fan, drifting away from the sun, curving gently under light pressure. That's the usual behavior, but deep field imagery revealed something backward. The trail arced against the expected flow, a reverse sweep. At first, people suspected processing errors, starfield subtraction, angle registration, filter, artifacts. Yet, independent teams in Chile, Spain, Japan reported the same geometry. The dust wasn't obeying the simple photonic script, it was being shaped by something else. It helps to remember the 2 tails, dust tail, guided mainly by radiation pressure, and gravity, ion tail, guided by the solar wind's magnetic field. Both usually extend away from the sun, but diverge slightly. Atlas seemed to defy both categories. Its trail bent laterally, not radially, as if pulled along invisible arcs. High-contrast imaging revealed more detail. The dust wasn't dispersing as a simple cloud. It arranged into layers, faint striations, like ripples on water, each layer suggesting particles of specific size and charge. Smaller grains should have raced outward fastest, yet they clumped into linear filaments, holding spacing with uncanny stiffness. When analysts reconstructed the shape in 3D, those filaments formed a twisting ribbon, a helix coiling behind the nucleus. The same basic geometry seen in 2014, the earlier spiral jet, only larger. And that led to a startling hypothesis: the dust trail was magnetically organized, as if the comet's plasma environment imprinted field structure onto escaping particles, arranging them into ordered strands rather than letting them scatter. If true, then Atlas wasn't only responding to the sun's field, it was briefly shaping its local magnetic geometry through induced magnetism. Researchers at ESAC ran combined simulations, plasma, dynamics plus radiation pressure, and the results were unsettlingly close. Even a weak residual magnetic moment, around 1/10,000th of Earth's, could create streamlines that trap charged dust along curved paths, bending opposite the radiation flow with a beta-flacket. Slight rotation around the comet's trajectory. Spectroscopy added another clue. Polarized emission oscillated in a way consistent with alignment, like filings around a bar magnet, yet the grains were mostly non-metallic, carbonaceous, silicate-based, suggesting the ordering wasn't inside the particles, but imposed by an external electromagnetic environment. For a short window after the burst, the region around Atlas may have acted like a magnetized bubble, quietly choreographing, each escaping grain, and the persistence was notable. Typical dust tails diffuse quickly, but this structure stayed sharply defined for days, a double helix pattern that refused to unravel. That coherence implies tension, magnetic, or electrostatic, or both, holding the filaments together against dispersive forces. In effect, the trail behaved less like inert dust and more like a plasma filament. Observers compared it to Birkeland currents, those vast, twisted plasma, threads that link stars and planets. On a smaller stage, Atlas seemed to generate its own version. If that's right, it may be the first strong evidence of interstellar material producing self-organized electromagnetic structures inside the heliosphere. Eventually, the coherence weakened by about 0.5 astronomical units from the sun. The filaments began to fray, the pattern softened, and the trail drifted toward a more conventional look. But by then, the signature had already been captured. Official bulletins stayed careful, calling it anisotropic dust, dispersion under transient magnetic influence, safe words, measured words. Yet among those who watched the raw frames, another thought circulates, quieter, persistent, that Atlas briefly demonstrated how dust can become order. When guided by electromagnetic harmony, the trail wasn't only residue, it was choreography, geometry written in carbon and light, spiraling through space like a fingerprint of invisible forces. Not proof of intention, but proof that the universe can still surprise us, with structure where we expect scatter. And perhaps the strangest clue of all came not from what telescopes saw, but from what timing revealed. A change in the comet's spin. Before perihelion, its rotation period was measured near 8.6 seconds, a precise photometric pulse, steady and repeatable. After the burst, that period stretched to nearly 9.7 seconds, a slowdown of more than 12% in mere hours. For a kilometer-scale interstellar object, that is almost unthinkable. Yet observatories in Chile, Japan, Spain all converged on the same conclusion. 3. Atlas had lost angular momentum. Comets can change spin, but typically slowly, and for familiar reasons. Jets act like tiny thrusters, speeding or breaking rotation, depending on orientation. We've seen it before. Comet 67P, studied by Rosetta, shifted its spin by minutes over months from outgassing torques, but Atlas changed by seconds in a single day. And that difference is where the mystery deepens. Comets can change how fast they spin, but usually it happens slowly and for reasons we can map. When gas slips away from a rotating nucleus, those escaping jets behave like tiny thrusters. They can nudge the spin forward or back, depending on where they vent and which way they push. Rosetta showed this with Comet 67P, its rotation shifting by minutes over months, a gentle drift powered by steady outgassing. But 3 Atlas was different, a 12% slowdown in a single day, not a slow drift, a dramatic break, far beyond the usual playbook. Something stronger and stranger seemed to reach into the motion and pull. The first explanation returned to one word: symmetry. That outburst near the sun didn't resemble a single vent. It looked like many fissures waking together, gas and dust releasing almost at once. If enough jets fired in the right configuration, opposing the direction of rotation, they could cancel angular momentum, like pushing against a spinning wheel in perfect timing. But the required energy is hard to swallow. The kind of coordinated braking that on paper resembles multiple megatons of force delivered in synchronized opposition. A fragile nucleus should have fractured under that stress, and yet 3 Atlas remained intact, quiet, almost composed, continuing its path as if nothing had torn inside it. That calm survival opened another door. Maybe the slowdown wasn't purely mechanical at all. Maybe it wasn't jets, but fields. During the burst, Atlas moved through magnetized plasma, and if it carried conductive material, metallic inclusions, carbon-rich lattices, anything able to carry current, then the sun's environment could have applied a different kind of brake. In physics, there's a familiar idea: magnetic braking. A conductor moving through a magnetic field can develop induced currents, and those currents create forces that resist motion on Earth. We use this principle in train systems: smooth, contactless, controlled. In space, under the right plasma conditions, it could slow a rotating body without touching it. The case strengthened when Parker data was reviewed right during the spin change. Magnetic flux density shifted sharply, then settled into a new configuration, like a circuit completing and stabilizing. A pattern consistent with induced current behavior, not just random turbulence. If the coma briefly behaved like a conductive sheath, it might have transformed rotation into other forms of energy: heat, electromagnetic radiation, subtle emissions. In simple terms, angular momentum could be bled into space. A quiet conversion rather than a violent breakup. And infrared readings added a gentle hint. Post-burst cooling happened faster than expected, as if internal energy had been redistributed and released. Some models imagined layered structure, conductive bands, beside insulating layers. A pattern that could support a large current pulse, forming circulating currents, eddies, that slow rotation while spreading heat through the shell. Still, even this doesn't fully explain the elegance of the change, because the slowdown wasn't messy, not jagged, not irregular. The light curve suggests a smooth deceleration over roughly 30 minutes, then a stable new period. No tumbling, no wobble, no fragmentation signatures. It felt almost like easing into a lower gear. Dynamicists noticed something else. The new rotation rate sat unusually close to the sun's local magnetic oscillation rhythm in that region of the heliosphere. It could be coincidence, but the alignment is uncomfortably neat, like a resonant lock, a pendulum, settling into the tempo of a driving force. If that's what happened, it would be the first recorded case of an interstellar body temporarily coupling its rotation to solar plasma waves. A brief synchronization, not of intention, but of physics. Skeptics remain cautious, preferring rare feedback between outgassing and geometry. Yet even they admit no known comet has slowed so quickly, so evenly, and survived whole. And so the spin drop stays, one of the cleanest riddles in the Atlas record, physics bending, without snapping, a traveler from another star system seeming to feel our sun's pulse and quietly answering by slowing. When post-perihelion spectra were assembled, researchers expected a familiar signature: hydrogen, oxygen, hydroxyl radicals, the usual water-driven chorus that brightens near the sun. But one hallmark wasn't merely faint, it was absent. The hydrogen alpha band, normally unmistakable during close solar heating, was silent, not hidden, not diluted, simply missing. At first, teams considered instrument limits, glare saturation, geometry, poor angles, the easy explanations we reach for at midnight. But follow-up data refused to change. Solar, orbiter, Parker, and even Hubble comparisons all pointed the same way. Water signatures weren't showing up. Instead, carbon dioxide bands dominated, oxygen ions stood out, and faint molecular nitrogen traces appeared. 3 Atlas carried almost no hydrogen signal at all. That's more than chemistry, it's an origin clue. In our solar system, comets are ancient water vaults, formed where hydrogen and oxygen readily froze into ice. Hydrogen is also the first thing to disappear in warm, active environments. So, an interstellar body arriving hydrogen quiet suggests either a very different birthplace or a very long history of stripping and loss. 2 main ideas formed, softly, cautiously. First, Atlas may have formed where water never dominated. perhaps in a carbon-rich, volatile pore disk with ices like CO2, methane, nitrogen, rather than water. That kind of chemistry could yield a denser, tougher object, and it matches its unusual composure near our sun. The second idea is stranger, but still natural. Maybe it once had water and lost hydrogen gradually during interstellar travel. Cosmic rays, plasma shocks, radiation bombardment over millions of years can sputter away lighter elements, leaving heavier oxides and carbon-bearing compounds behind. A mineralized remnant, the core of something that used to be wetter. Yet even that leaves a question, because the coma was bright in oxygen emissions, if not from water. Breakup. Where did that oxygen come from? Some suggested superoxides or peroxides embedded in the crust, breaking apart under heat, releasing O2 directly. Others pointed toward high-energy photons, splitting carbon dioxide into oxygen plasma, a process that doesn't require hydrogen at all. That possibility shifts the feel of the whole event, from thermal venting to electrical behavior, from simple evaporation to charge and discharge. It also harmonizes with what we saw earlier: magnetic, resonance, shock signatures, plasma structure. Without hydrogen, charge balance changes, potentials can build differently, and release can become sharp, even abrupt. In that sense, missing hydrogen isn't a footnote, it could be a key, shaping the symmetry, the shell, the die, coherent jets, the way Atlas reacted under stress, and the way it refused to fragment like ordinary comets. The absence also feels cosmically odd. Hydrogen is everywhere, the universe's most common element, so finding a body that appears so depleted is like hearing a song missing its deepest note. It challenges the quiet assumption that interstellar debris is compositionally standard. Maybe this object is a relic of a rare environment, older, metal-rich, chemically unusual, or forged in conditions where hydrogen chemistry never took hold. Whatever the birthplace, its physical consequences are practical. No water ice means no classic water-driven jets, so the bursts, the pulses, the shockwave must come from other volatiles, especially carbon dioxide and oxygen-bearing species. And when those gases are ionized, their behavior can become more energetic and more ordered than the dusty water comets we grew up modeling. Looking back, the hydrogen silence ties, threads together, the density paradox, the metallic-like reflectivity hints, the stability under solar stress. Even the lack of catastrophic breakup could fit a body with little accessible water left. Inside, a chemically hardened traveler, less prone to the familiar crumbling fate. To scientists, absence isn't emptiness, it's information. Atlas's missing hydrogen may be telling us it carries the memory of a different kind of star, system, a different chemistry, and perhaps a different set of behaviors when exposed to intense plasma. In the quiet gap between spectral lines, there may be the faintest fingerprint of an origin, stranger than the sun, and older than our easy assumptions. And when natural, explanations began to stretch thin, one uncomfortable idea resurfaced, not loudly, not in headlines, but in hushed conversations and careful wording. What if 3 Atlas isn't entirely natural, not aliens, not intent, just a question about structure and origin? The phrase artificial hypothesis appeared quietly in a closed internal memo at ESAC 3 days after perihelion, written by an engineer, not an astronomer, focused on the stubborn precision of patterns, the spiral jet, the geometric alignments, the stable substructures. The language was restrained, but the meaning was clear. We are seeing order that is hard to get from random breakup alone. At first, most dismissed it. At first, gently. Every field has its fringe, its late-night emails, but as more anomalies stacked up, timing with the CME, the resonant-like magnetic oscillations, the persistent geometry of reflective points, laughter softened into silence. The cautious version of this hypothesis doesn't claim purpose. It simply asks, could this be manufactured material, a fragment of older technology, a remnant, a casing, a component, drifting for ages, inert, until our sun's field stimulated, pays it into response? Most scientists still dislike the idea because it threatens clean categories and because extraordinary claims demand extraordinary proof, yet the numbers keep irritating the edges. trajectory stability remained unusually tidy, even after energetic events, no significant wobble, no chaotic tumble. That kind of composure implies either high mass concentration or some other stabilizing mechanism we haven't pinned down. Then there's reflectivity. Post-burst behavior looked oddly directional, a brightening within specific solar angles, suggesting specular reflection, like smooth surfaces rather than dusty foam. Some models noted that certain crystalline or composite geometries could reproduce that angular behavior. Not proof, just an echo of possibility. And the spiral jet, again, timed to the spin with unnerving steadiness, stable across multiple revolutions. Ordinary vents drift, choke, fluctuate. But this structure held its pattern, like a steady exhaust, pulsed, repeating, consistent. The magnetic coupling only deepened the tension. Atlas didn't respond with obvious chaos. It responded with rhythm, almost like inductive transfer. Energy exchanged between fields, the way wireless systems share power across distance. Not a message, but a mechanism that behaves cleanly when stimulated. Officially, the idea remains unaccepted, because the natural explanations aren't fully exhausted, and because restraint is part of the scientific muscle. Yet paradoxically, the simplest natural models kept failing to reproduce the whole set, missing hydrogen, density contradictions, and that elegant, rapid spin drop. Some teams built detailed simulations to disprove it, reshaping nuclei, changing porosity, tuning outgassing, testing fracture scenarios under solar load, and still, the observed stability was hard to recreate. One speculative model noted that honeycomb-like internal structure could explain certain inertia and thermal properties. A coincidence? Maybe, but one that refused to disappear entirely. By December 2025, a brief anonymous note appeared online and vanished quickly, suggesting a momentary coherent reflection during the blackout window. Structured? Possibly. Composite? No peer-reviewed follow-up emerged, and without verification, it remains only a rumor-shaped shadow. But even rumors grow loud when real data has gaps. To most, the artificial hypothesis is a thought experiment, a way to pressure test our physics, a reminder to separate pattern finding from proof. Yet to a small minority, it's an uncomfortable possibility that we're watching a decayed technological relic, long dead, yet still mechanically reactive under solar forcing. If it were artificial, its purpose might be unknowable: propulsion debris, probe casing, structural remnant, something built long ago, now drifting without context, awakened only by electromagnetic stimulation near a star. There is still no confirmation, only geometry, timing, and persistence. Patterns too clean to ignore, but not clean enough to declare. And beneath it all, an older question: how do we tell complex nature from forgotten design, especially when both can produce beauty? Maybe the answer isn't certainty, maybe it's patience and the willingness to sit with ambiguity without forcing it into a story too quickly. Because sometimes the oldest secrets aren't hidden behind dust, they're hidden in plain structure, in the line between chaos and construction, a line our minds keep trying to sharpen. Another pressure point emerged when teams tried to balance the energy budget. Every event has accounting. Something feeds it. Something radiates. Something remains. But with Atlas, the ledger didn't behave. Light, heat, ionization, kinetic effects. The output appeared to exceed the input by orders of magnitude. Early comparisons were blunt. Given its size and reflectivity, the nucleus could absorb only so much solar energy during closest approach, and yet the burst radiated far more. Even when accounting for phase change energy from carbon dioxide or carbon monoxide, the numbers still wouldn't settle, which means sunlight alone couldn't be the whole fuel. Sublimation can release stored energy pathways, but it doesn't magically create energy. So researchers looked for stored potential, pressurized volatiles, chemical reactions, internal reservoirs. Yet density models argued against huge empty cavities, and the object showed no pre-burst instability, no obvious tremor of impending breakup, and the character of the emission offered a clue. The spectral lines weren't purely thermal, they carried non-thermal components. signatures consistent with particle acceleration. That pushes the story toward plasma processes and toward electricity. In that picture, the CME becomes more than a gust. It becomes a magnetic pulse. An atlas becomes a temporary, electrical participant, currents induced through conductive regions, a brief connection to the sun's circuit. The burst then reads less like an explosion and more like a discharge, a rapid equalization of charge. The coma turned into a kind of capacitor-like shell, holding electromagnetic energy momentarily, then releasing it as light, heat, and ionized outflow. The shape of the brightness curve even fits that mood fast. Rise, symmetrical decay, like a system snapping back toward equilibrium. But that model demands one more uncomfortable ingredient: high conductivity, far beyond porous ice and dusty rock, suggesting metallic grains, carbon-rich frameworks, or semiconductive structures able to carry current efficiently, a nucleus that behaves more like an electrical material than a simple frozen aggregate. Analysts cross-checked timing with Parker's field data and found a short phase delay between the CME's magnetic front and the luminosity surge, a delay consistent with inductive coupling across a plasma region thousands of kilometers wide. Again, not proof, but another piece that points toward electromagnetics. When they reframed the energy budget in terms of current, the numbers finally began to balance, but only under extreme conditions. Current densities large enough to rival powerful terrestrial discharges, enough to produce momentary brilliance without requiring the nucleus to shatter. The result is an unsettling shift in how we describe comets, not only as passive bodies eroded by sunlight, but as possible active nodes in a star's plasma environment, interacting, storing, releasing, briefly shaping the space around them. Still, not everything fits neatly. Some faint emissions appeared at frequencies that don't match common plasma transitions, subtle harmonics, repeating in clean ratios, hinting at resonance, feedback loops, amplification beyond simple induction. And that's where the story remains, balanced on the edge of explanation, not declaring design, not surrendering to mystery, but listening closely to what the data suggests, in the calmest possible way. Because, with 3 Atlas, even the accounting of energy feels like another soft riddle, a reminder that the sun is not only light and heat, but a vast electromagnetic presence, and this interstellar traveler, for a moment, may have learned how to answer it. If that ever gets confirmed, it would mean 3 Atlas, briefly, slipped into an unstable electromagnetic ring, an oscillation that let it draw extra power from the solar wind around it, not just reflecting sunlight, but momentarily tapping the flowing charge in space. For a few minutes on October 29th, this interstellar visitor may have acted like a tiny auxiliary dynamo, taking the sun's energy stream and returning it as light, heat, and ionized plasma. And when it ended, the top object cooled again. Whatever internal behavior was active went quiet. In the end, the energy budget becomes less like bookkeeping and more like a gentle philosophical pressure. Can a small body, for a moment, behave like a generator inside a star's wider circuitry? If the answer is yes, then what we witnessed wasn't a broken law. It was a lesson that the cosmos is not isolated stones in empty, dark, but a living web of currents, rhythm, and connection. In the weeks after the burst, something else appeared, softer but persistent, a faint cadence in the way Atlas returned sunlight, not random glitter, not simple rotation shading, but a repeating pattern, measurable, steady, almost patient. Researchers began calling it a photon, reflection, rhythm, an optical modulation that felt less like glint and more like an echo in light. The earliest strong detection came from Subaru in Hawaii, where high-speed photometry revealed pulses every 19.4 seconds. Very subtle, less than 2% variation, yet too consistent to dismiss as noise. Soon after, the Very Large Telescope in Chile saw the same timing, the same gentle beat. And that confirmation mattered, because it meant the rhythm belonged to Atlas, not the instruments. In other words, 3 Atlas was reflecting light with a dependable interval, a quiet metronome in the glare, not loud enough to dazzle, but steady enough to be counted frame after frame, as if the surface had learned a small, repeating motion. At first, the simplest thought was rotation, sunlight catching ridges, facets, or sharp angles, but the measured spin, after the slowdown, sat near 7 seconds, and the optical rhythm didn't match it. It landed almost exactly at double, and that mismatch opened the door to new explanations. One idea suggested two opposing reflective zones, twin patches, flashing in alternation as the nucleus turned, creating a doubled period, like a lighthouse with two lamps. Another possibility drifted into view, that the light wasn't purely reflected, but partly re-emitted from ionized gas, whose brightness rose and fell with waves in the surrounding plasma field. Spectra added a finer twist. The pulses weren't identical across all wavelengths. In visible light, the modulation looked gentle, almost smooth, but in near-infrared, the W's, peaks sharpened, more crisp, almost staccato, as though the material favored certain bands, amplifying some frequencies more efficiently than others. That behavior can resemble photonic mirrors, crystalline lattices, layered composites, structured films, things we usually associate with engineered optics, not ordinary ice and dust. And yet, images after perihelion didn't show a clean, polished sphere. They showed a fractured crust, angular ridges, mixed frost and mineral composites, the phoster, kind of surface that can, under stress, reorganize in surprising ways. If those fractures briefly crystallized, under heat, compression, and magnetic forcing, they could form microscopic diffraction grids, tiny repeating structures that bend and return light, in patterned interference, a natural effect, but highly ordered, the universe building, for a short time, its own quiet photonic circuit. To test that, a Max Planck team ran simulations of polarized scattering through carbon silicate mixtures under magnetic compression, and the modeled curves lined up strikingly well. Layered carbon dioxide ice, in strong fields, can reorganize into quasi-crystalline textures that produce repeating harmonic intervals. The same simulations also predicted the 2-1 relationship, rotation, coupled to an external oscillation, a dance between matter and field, where the surface response repeats every other turn, not because it decides, but because the physics locks into a stable cadence. Still, not everyone felt satisfied, because the pulses stayed coherent, not drifting, not smearing out, for more than 48 hours, even as distance and geometry shifted. That level of stability is uncommon in messy natural systems, and it revived, quietly, the more speculative ideas, including the thought of a passive optical beacon, not proven, but hard for some to ignore. Others noticed a different coincidence. 4 seconds sits close to plasma resonance timescales, measured near the object during the magnetic coupling phase, so maybe the surface wasn't signaling, maybe it was simply ringing, like a bell that continues to hum after the strike has passed. The rhythm also had direction. Its amplitude changed with viewing angle, and rose sharply near a phase offset around 37 degrees, an angle often associated with specular reflection, the kind you see from glassy or metallic-like layers. This supported the idea that the burst melted, refroze, and vitrified parts of the crust, turning small regions into transient mirrors. By mid-November, a blended model gained popularity, a photonic skin, a semi-crystalline CO2 glass shell, seeded with silicate dust, periodically charged, then relaxed, by the nearby plasma. Each relaxation could momentarily realign molecules, boosting reflectivity at selected wavelengths, and producing that completely steady optical beat. It sounds poetic, but the implication is technical. The boundary around Atlas wasn't passive, it behaved dynamically. It didn't only bounce light back, it modulated it, shaping the return signal through resonance, through structure, through charge. And so the photon reflection rhythm became more than a footnote. It reminded observers, gently, that reflection can carry pattern, and pattern can carry information, not necessarily a message, but a fingerprint, a readable consequence of how light and plasma, sometimes, what matters isn't the brightness itself, but the timing, the harmonics, the way the light comes back, as if the interstellar traveler briefly whispered to the sun in pulses, and our instruments, for a short window, were able to. Listen, when the burst happened near the Sun, nearly every inner system instrument captured something. Solar Orbiter saw the flash. Parker recorded magnetic compression. Ground stations logged a faint radio echo. But one unexpected source went strangely quiet. Mars. For almost 12 hours beginning October 29th, 2025, telemetry from Mars orbiting platforms became incomplete. Not a total blackout, more like a selective silence. Instruments that track ionospheric density and magnetic flux stopped returning meaningful readings, while cameras and spectrometers continued as normal. NASA's Deep Space Network flagged the anomaly in real time. MAVEN, monitoring Mars since 2014, lost ion and electron counts at 1,440 UTC. Right as the Atlas burst peaked behind the Sun, then the stream resumed at 0256 UTC the next morning. No damage, no power fault, no radiation spike, almost as if the sensors had been briefly washed clean. A solar storm would be the easy blame, but none appeared. The CME tied to Atlas was weak and localized, not the kind of system-wide hammer that should blind Mars. And yet, across multiple missions, the same category of field and ionosphere data dropped out together, while other telemetry stayed steady. It didn't look like a battery problem, it looked like a physics layer problem, because the ionosphere is that fragile boundary where atmosphere thins into space, shaped by the solar wind like a slow-moving tide. It glows faintly in ultraviolet, it ripples. Under pressure, it acts like a natural space weather membrane, and during the Atlas event, that membrane went unreadable. No charge density structure, no clean magnetic vectors, almost as though the gradients flattened. When the data returned, there was an overshoot, ion density, spiking to nearly 10 times normal, then settling quickly, more like a delayed reboot than a gradual recovery. The timeline offered a quiet hint. The main plasma burst near the Sun was pinned near 1,437 UTC. The same minute Mars's field count instruments dropped. Mars was about 200 million kilometers away, too far for a mechanical wave, but not too far for an electromagnetic disturbance riding the solar wind, and the 12-hour window matches the travel time of a solar wind-borne magnetic ripple moving outward at typical speeds, so the gap may not have been instrument failure at all. It may have been the environment itself changing, Mars's upper atmosphere temporarily shifting into a quieter state until the pulse passed. If that interpretation holds, then Atlas launched a field disturbance strong enough to smooth the very gradients those sensors measure, a temporary neutralization, not of Mars as a planet, but of the thin electromagnetic structure around it, a planetary scale echo written in silence. It sounds unbelievable, but there is a distant precedent. During strong solar events, Earth's magnetometers have briefly struggled when field vectors shift faster than calibration can track. Yet those are sun-driven storms. For a comet, even an interstellar one, to contribute from so far away would require an unusually coherent pulse, something we don't normally assign to small bodies. Theories arrived quickly. One suggested an Alphen wave, a magnetic shock carried through plasma, launched by the comet's discharge and intersecting Mars's orbit like a passing ripple. As it crossed Mars's induced magnetosphere, it could have equalized charge globally, flattening differential readings and making sensors see nothing. Another idea focused on geometry, alignment. Mars positioned along a favorable field line, a resonant target for the passing disturbance. Whatever the cause, the implication is gentle but enormous. Atlas didn't only absorb and glow, it redistributed energy through the heliosphere in a way that could be measured far away. And one more eerie detail appeared in follow-up. MAVEN's ultraviolet data showed faint residual fluctuations with a cadence reminiscent of the photon reflection rhythm near Atlas, as if the signature passed Mars and continued outward, leaving no crater, no dust, no visible scar, only a gap, a silence, recorded in magnetic history. To this day, the Mars data gap remains one of the strangest puzzles. In a solar system full of constant noise, Mars experienced a stretch of quiet, as if the planet took a breath, in step with a visitor from another star. Coincidence, resonance, or a deeper coupling, no one can say with certainty. But the silence still suggests one calm truth. Even across millions of kilometers, the solar system can behave like a connected instrument, and a single event can ripple through places we don't expect. By mid-November 2025, 3 Atlas had climbed away from the sun's deep grip, headed outward, toward interstellar darkness again. Normally, comets fade gradually here, activity softening as warmth declines. But with Atlas, something stranger happened. It didn't dim the usual way. It seemed to shut down, almost overnight. Multiple teams reported the same shift. No tail structure, no clear plasma signature, no radio echo, as if the object had powered down. Astronomers began calling it the outbound silence, and at first, many assumed it was simply distance, until the timing refused to match the math. The cutoff came too suddenly, not a gentle fade, but a steep cliff in the light curve. One observing run still showed faint, steady CO2 lines, and the next, nothing at all. Infrared, radio, even the broader electromagnetic signature fell straight back into background, and the reflected sunlight that had defined its visible presence dropped below detection far too quickly, nearly 3 times faster than the distance math predicted. So, theories spread fast, like whispers in a dark control room. Some argued the visitor had finally spent its volatile fuel, sealed under a vitrified skin, carbon and silicate fused into glass. Others wondered if it had broken apart into dull fragments too small and too dark to track. But ESA's heliospheric imaging still hinted at a coherent gravitational trace. Mass was still behaving like mass, meaning the body hadn't simply disappeared. It was still there, just no longer speaking in light. Then came a stranger clue. Days later, Parker detected a faint, lingering depression in plasma density behind Atlas's outbound path. A wake, a thin corridor where solar wind particles looked displaced and somehow not replenished, as if the object had carried something away. With it, a pocket of charge, a bite taken from the flow. A wake like that shouldn't hold its shape for long, hours, maybe not days, yet it persisted, drifting outward like a hollow channel in the wind. That corridor became an obsession. Reconstructed field maps suggested low electron counts and an almost unnerving, magnetic smoothness. A uniformity rarely seen so close to the sun, where turbulence is normally constant and restless. The region measured nearly neutral. No strong polarity swings, no noisy fluctuations, no obvious reflections. A pocket of quiet space. Some compared it to the shadow behind ion drive spacecraft, where charge flows and exhaust can briefly sculpt calmer plasma behind them. But Atlas wasn't running an engine, and it wasn't supposed to be capable of that kind of order. That contradiction pulled attention toward a different idea, that the silence wasn't only physical, it was electromagnetic, a transition into a stable, non-interacting state, charge fully neutralized, resonance damped, the object's potential matching the surrounding solar wind so closely that it lost contrast, and, in losing contrast, it vanished from the instruments that needed it. And during this same stretch, radio astronomers, hunting the faint reflection rhythm, found something even more unsettling than a weak signal. They found its total absence. The harmonics that had pulsed for weeks didn't fade. They were simply gone. The 20 to 40 megahertz band, once textured with modulation, flattened into a clean line, not static, not interference, but a silence so smooth some described it as too perfect. A quiet, so complete it felt almost manufactured. People couldn't help remembering 2017, when Oumuamua also slipped away in a way that felt abrupt. But this was deeper, broader, optical, electromagnetic, and reflective signatures, all disengaging together as if the visitor had released its last response and then stepped back. Plasma physicists offered a careful mechanism, a resonant shutdown, after enough charge exchange. The surface and coma may have reached equilibrium, no net ionization, no differential potential, no contrast for sensors to hold on to. In that state, Atlas wouldn't shine to our detectors, even if it still existed and still moved. It would be present, but electromagnetically quiet. Others, more speculative, used a softer word, hibernation, a self-protective mode, a stabilizing shift meant to preserve structure as it headed back toward deep space. No proof, just an uneasy fit with the pattern, because the story now had a strange symmetry of its own. Atlas entered our system loud, bright, reactive, and left it in a stillness that felt like completion. It arrived in plasma and geometry, and departed as if an electrical loop had closed, charge, discharge, return to ground. And whatever caused it, the emotional effect was undeniable. A visitor that seemed to choose silence after speaking too brightly near the sun. By late December, even the biggest telescopes struggled. No clean optical confirmation, no steady radio trace, only the faintest gravitational hint in the numbers suggesting it continued outward, intact. For scientists, the outbound silence became the final unsolved equation. An interstellar traveler that burned too bright, released too much, and then without a slow decay turned off. And inside the archive, one detail kept returning: the simultaneity. Every anomaly burst, resonance, reflection, rhythm ended together within seconds, not like a dying ember, but like a switch being flipped. The universe is usually noisy when it moves. Stars hum, plasma murmurs, particles chatter. Yet for one moment in late 2025, as 3 Atlas crossed into the outer flow, everything connected to it, from photons to plasma, went still. And that, more than the flare, may be the most unsettling part, because sometimes the loudest statement nature can make is perfect silence. By December 2025, teams merged everything into a single compiled record, the most complete dossier ever assembled on an interstellar visitor, petabytes of measurements, thousands of pages of analyses and cross-checks. And still, one question remained: what exactly had we witnessed? So scientists began to call it simply the anomaly, not as a dramatic label, but as a technical one. In science, an anomaly is a measured deviation that refuses to fit expectation, yet repeats cleanly enough to demand explanation. And the Atlas anomaly had layers, each documented, each stubborn, each incompatible with ordinary comet physics. It began with the burst, brightness beyond thermodynamic comfort, then the CME timing, the plasma interaction that lined up too neatly, then the missing frames, the density paradox, the spiral jet, the shock-like pulse, the hydrogen, quiet, and finally, the outbound silence. No single framework held them all at once, so the summary reports began grouping them, not by story, but by measurement. Many analysts described 3 overlapping strata: energetic, magnetic, and optical. The energetic layer centered on the impossible ledger, how the burst seemed to radiate more than sunlight could supply to a body of that size. Thermal models, sublimation curves, pressure release scenarios kept failing by uncomfortable margins. Only electromagnetic coupling could make the numbers behave, a picture where the object acted like a conductor inside a changing field. But that demanded conductivity far beyond porous ice and rubble, suggesting carbon, frameworks, metallic grains, or semiconducting structures. In that view, Atlas wasn't behaving like a snowball, it was behaving like a plasma node. The magnetic layer was stranger still, a resonance signature, synchronized to rotation, lasting about 12 minutes, then collapsing and leaving behind a measurable pulse in the solar wind. A star and a kilometer-scale body briefly sharing a frequency has no clear precedent in our catalogues, and the ripple hints extended outward, all the way to the Mars data void, where instruments went blank as if gradients had flattened. The waveform reconstructions looked like damped oscillations, structured, coherent, the kind of curve engineers recognize immediately, even if space rarely offers it so neatly. Then came the optical layer, the reflectivity shift, the polarized changes, the photonic rhythm, and the sudden vanishing act. Post-burst polarization suggested restructuring, not just melting or dust, a loss, but a surface changing how it scattered light, as if the crust briefly reorganized at a microscopic level to redirect photons rather than merely scatter them. Put together, the 3 layers didn't feel like one accident. They felt like a cascade, staged behavior, a sequence of responses followed by stabilization. In physics language, it resembles feedback regulation, systems adjusting through interaction with an external driver, the hallmark of many self-balancing processes. Most scientists still stop short of calling it artificial. Instead, Some floated a careful phrase, a coherent natural system, a body capable of internal order through feedback with solar plasma conditions. Under that interpretation, Atlas wasn't alive and wasn't designed, just born from unfamiliar astrophysical conditions. Magnetized carbon structures, volatile layers, able to store and release energy like a capacitor in a circuit. Others kept the uncomfortable alternative in the margins, the artificial hypothesis, resurfacing, quietly, because the pattern resembled control logic, input, amplification, stabilization, shut-off. The physics could describe it, but description didn't feel like explanation. When review groups met in late December, their language stayed cautious. Evidence balanced with humility. They framed it as an interstellar object showing coherent electromagnetic and optical behavior, inconsistent with known cometary mechanisms, with uncertain classification. In plain terms, a formal admission that the visitor fit no clean category, comet, asteroid, or something in between. As Atlas faded beyond reach, one final question lingered. Was this a one-time alignment, or a behavior common to interstellar matter we've simply never had the chance to witness up close? The honest answer is waiting. Somewhere beyond the heliosphere, 3 Atlas continues outward, silent, intact, data etched into every arc of its path. Its strange gift isn't that it refused explanation, but that it followed a logic just a little ahead of our ability to decode. And in the end, the word anomaly became a boundary, not a conclusion, the line where certainty ends and wonder begins. And if you enjoyed drifting through this mystery with me tonight, come back again, whenever you need a quiet sky to rest beneath. Because, here, we'll keep following the strange visitors, the soft signals, and the unanswered patterns, one calm story at a time. If you'd like to support Bedtime Talks, tap subscribe so you don't miss the next late night journey. Leave a gentle comment below. Tell me where you're listening from and what time it is for you right now. I love seeing how far this quiet community reaches. And if this story brought you even a little peace, you can give the video a like. It helps these slow, soothing mysteries find the people who need them. For now, settle deeper into your pillow, let your breathing slow, and let the universe do what it always does. Move quietly, far beyond our windows. Good night, and I'll see you in the next Bedtime Talks.